Hello. In this video we're going to look at the idea of expected value. And expected value is a way to measure what you think is going to happen over a long period of time. Especially if, let's say, you're playing a game over and over again, or you want to know whether a game is fair or not. Those are some places where expected value is quite helpful. So let's go ahead and get started with the notes. Okay, so here's this section, and the first thing I want to ask is, what is expected value? And the way I would describe expected value is it is what happens on average over the long run. If you're conducting some experiment over and over and over and over again, what on average is going to happen over the long run? So here's an example. I've got two die, and I'm going to roll them, and my sums are, here's my possibilities. And then I went to my table that had the different ways that those sums can happen, and I came up with the probabilities of each of those. Because what I want to answer is the question, what is the expected value of the sum of two dice? So here's how I'm going to do this. In order to find the expected value, I do the following. You multiply each outcome by its probability. So take each outcome, multiply it by the probability of that outcome occurring, and then add all products together. Alrighty? So if I want to know the expected value of the sum of two dice, what I'm going to do is I'm going to take each outcome, multiply it by its probability. So I could have a 2, and the probability of that is 1/36. I could have a 3, and the probability of that is 2/36. I could have a 4, and the probability of that is 3/36. And I'm adding all these together, and I'm going to keep going through all those different possibilities. Now what I'd like to do is I'd like to do that quickly on the calculator. And so what I notice is I've got a common denominator of 36 all the way across. My numerators are going to be 2 times 1, 3 times 2, 4 times 3, 5 times 4, 6 times 5, 7 times 6, 8 times 5, 9 times 4, 10 times 3, 11 times 2, and 12 times 1. And so I'm going to do all the the numerators first. 2 plus 3 times 2 plus 4 times 3 plus 5 times 4, etc., etc., etc. My numerators come out to be 252. I have a common denominator of 36 all the way across, so that's going to give me a 36 here. And then I divide those, 252 divided by 36, and I get that my expected value of rolling two dice and looking at the sum is 7, which means on average, in the long run, my average value when I roll two dice is going to be 7, which makes pretty good sense, because if you look over here, 7 is the one that occurs with the most frequency, and everything else is symmetrical around 7. So if you look at the 10 and the 4, they both have the same probability, so they'll show up the same number of times, and they average out to 7. So that's how we do expected value. We just multiply each outcome times its probability, and then add all of those together. So let's look at the first example here. It costs $2 to roll a pair of dice. If the number is odd, you win $1. And if it's either double ones or double sixes, you win $5. What's the expected value for the game, and is it fair? So to find the expected value, I'm going to do a little chart here. And my little chart is going to have three pieces. It's going to have outcomes, it's going to have the value of those outcomes, and it's going to have the probability of those outcomes. And I'll do that every single time I'm setting up expected value. So my outcomes are, I could have an odd. A second outcome is I could have double ones or sixes. And my third outcome is could be other, anything else. Now I want to look at the value of each of those. And there's two ways to look at the value. One way I could look at value is I could say, all right, if I get an odd number, I win $1. So I can think of that as a +1. Or the other way I could look at it is I've got to pay $2 to roll the dice in the first place. So if I get $1 back, I've actually lost $1. Okay, and I'm going to do this with both of them so you can kind of see how it works. The double ones or double sixes, you could look at it and say I win $5, so that's a +5. Or you could look at it and say, well, it cost me $2 to roll in the first place, so really I only won $3 overall. And then the other, if you get anything else, you don't win anything. Or you could say, hey, I already paid up $2, so I'm actually down $2. Alrighty? And then probability. Well, the number is odd. We've looked at that several times. It's 1836. Double ones or double sixes. Well, double ones would give us a 12. Double ones would give us a 2. Double sixes would give us a 12. So there's one of each of those. So that would be 236 for our probability. And then anything else. Well, let's see here. I've got 18 possibilities here, another 2 here. That's 20 possibilities out of the 36, which means 16 possibilities are left. Because all of these probabilities should add up to 1, because they all make up the sample space, and the probability of the sample space is 1. So now let's look at my expected value. And remember, I'm going to do this both ways. I'm going to do it first off with this first value. So my first value is a 1, and the probability of that is 1836. Plus my second outcome, the value of that is a 5, and my probability is 236. And my third outcome is a 0, and the probability is 1636. So when I do that, notice I'm going to get 18 plus 10. That's going to give me 2836. All right, so my value, 2836, is going to be about 0.78. So I'm going to, my expected value is about 78 cents. Now let's do expected value the other way, and then let's look at our two results and see what we can determine from them. If we do it the other way, we're going to use values of -1, probability of 1836, 3 and 236, and a -2 and 1636. And when we do that, we get -1 times 18, that's -18 plus 6 minus 32, and that comes out to be a -4436, which is about $-1.22. Now those expected values look very different. So what are they telling us? Well, in the first one, remember we said we were just looking at the end result, but we had this $2 pay-in. So it's saying, well, we're winning 78 cents on average over the long run, but if we're paying out $2, is it a fair game? No, we're losing money, aren't we? The second one says, I'm going to take that pay-in price into account, and I'm going to say that on average, I'm going to walk out losing $1.22. Notice if I say I'm losing $2 and I add 78 cents to it, I come up with the same value both ways. Okay? So when we ask, is it fair, we would say it is not fair. Because in order to be fair, what should our expected value be? Well, our expected value at the end of the day should be a 0. Notice if we did it this way, our expected value should have been a 2 so that the income matches the outflow. Right? But if we look at it down here, we would say that this is, if it was fair, that would equal 0. Okay, the income and the outflow would be the same. All right, let's look at the next example. In the next example, it costs $1 to play the lottery, where a player chooses a 3-digit number between and including 000 and 999. If the number is selected that day, then the player wins $500, which is a profit of $499, because they paid $1 to get in. Find the expected value of the game. Is the game fair? What should the price of a ticket be in order for the game to be fair? All righty. So let's set this up with our chart. And I'm going to have outcome. I'm going to have value. And I'm going to have probability. So our first outcome is we could win. All righty. And I'm going to use this second method so that I can go straight to whether it's fair or not. So if I'm winning, my value is going to be just my profit, okay, my $499. And the probability of that happening, well, there's 1,000 different numbers, and one of them is selected. So my probability is 1 out of 1,000. I could also lose. And the value there would be minus $1. And the probability of that happening is 999 over 1,000. So if I set up my expected value, that would be the value of winning, which is 499, times the probability of winning, which is 1/1000, minus 1 is my value for the next piece, times the probability of that happening, 999 out of 1,000. Okay, and when I multiply that out, I get negative 0.5. Since that's negative, I know it's not fair. So my second question is, what do I need to do to make it fair? Well, I could go ahead and just think this through logically. And I'm paying $1 in, and my expected value is I'm going to lose 50 cents. So if I took that off of the initial play-in, I would think that maybe 50 cents might work. But here's another way that we could do it. So let's set this up again. Okay, again, I'm going to have my outcomes and my values, and I'm going to have win or lose. But now what I'm going to do is I'm going to say, let's make my value of winning, well, I'm still going to have it be $500, but my value is going to be $500 minus what I pay to get in. And if I don't know what I'm paying to get in, I'm going to make that an X. And then the losing is going to be how much I paid in, because I don't get any of that back. So it's going to be a negative X. Okay? Just like up here, we had a 1, so 500 minus 1 gave us 499, and then a minus 1 is what we lost. We still have those same probabilities. And now, our expected value, if we want it to be fair, we want our expected value to be 0. And then we'll have 500 minus X times 1/1000 minus X times 999 1/1000. And now what I want to do is I want to solve that for X. So I just remember back to how we do this. I'm going to start by getting rid of the fractions. I'm going to multiply both sides by 1,000. And that's going to give me 1 times 500 minus x. 0 times 1,000 is 0. 1 times 500 minus x gives me 500 minus x. And then the 1,000 here will cancel with that, so it'll give me minus 999x. So minus x and minus 999x would give us minus 1,000x. So I'll add 1,000x to both sides. I'll get 1,000x equals 500. Divide both sides by 1,000, and I get x is equal to 0.5, or 50 cents, okay, which is kind of what we thought through up here. All right, so we can figure out how to make the game fair as well. All right, our last example says, based on mortality tables, the probability of a 20-year-old male living to age 21 is 0.99. If a $1,000 one-year term life policy on a 20-year-old male costs $25, what is its expected value? All right, so again, we start out with outcomes, the value of those outcomes, and the probability of those outcomes. So the outcomes, it's kind of morbid to say this, but the outcomes are that 20-year-old male could live or could die. The value, if they live, alrighty, then the value is negative $25 because they paid out a $25 for insurance and they didn't collect anything. If they die, it's going to be the $1,000 that they get back minus or their family gets back, minus the $25 that was paid in, so it's $975. The probability of living, we said, was 0.99. Okay, since these are well, I'm having trouble coming up with the word all of a sudden. Since those are complementary events, alrighty, they should add up to 1. So he's either living or dying, so that should be 0.1. And then our expected value is going to be the value of each outcome times the probability of each outcome plus 975 times 0.01. Alrighty, and when we do that in the calculator, our expected value is negative 15. So what does that tell us? Well, that tells us in the long run, if we pay for insurance on a whole bunch of hoax, that since the money's negative, that means that the insurance company is going to be making about $15 per person that's doing the insurance. Alrighty, so that's what our expected value will tell us. And lastly, I would suggest that you review or look at example 3 in the text. Okay, just another good example to kind of look at and walk through how that's working. So hopefully that helps with an understanding of what expected value is and how to use it.